area of the rectangle will be larger than the area below the curve on each given interval. And you can see why we include n plus 1. So we have the first term, the second term, the third, the fourth, up to the nth term. So we go, since we use n as the left endpoint of the interval, and use this x value to find the corresponding y value, the height of the rectangle, and we're going to the right, we need to consider the point n plus 1. And then it's clear that the total area of these rectangles will be larger than the exact area below the curve y equals 1 over x. Now, what is the area of each rectangle? Well, the width of each rectangle is equal to 1. And as the area is the base, the width times the height, then as the width, the base is always 1, then the area will be simply the height of each rectangle. Well, the function is 1 over x, so the height of the first rectangle is 1 over 1, which is 1. So the area of the first rectangle is 1. The second rectangle, the height is 1 over 2. So the area is 1 over 2 for the second rectangle. Third, 1 over 3. The fourth, 1 over 4. All the way up to the last rectangle, the nth rectangle, where the height is 1 over n. So the area is 1 over n. So look at this. The summation of the reciprocals of the first positive n integers is exactly equal to the area, the total area of these n rectangles. But clearly, this total area exceeds the exact area below the curve 1 over x. From x equals 1 to x equals n plus 1. We can now find the exact area below 1 over x from 1 to n plus 1 using the fundamental theorem of calculus. An antiderivative to 1 over x, of course, ln of x, can be evaluated from 1 to n plus 1. So we get ln of uppercase n plus 1. Then minus the ln of 1, which is 0. So all we have is the ln of uppercase n plus 1. And this is true for any choice of uppercase n. So look at the implication here. For any n, Sn is always at least as big as the ln of n plus 1. So what happens as we let uppercase n, the upper bound of summation, tend to positive infinity? Well, the ln of n plus 1, we know goes to infinity as n goes to infinity. So if Sn is always at least as big as ln of n plus 1, and as n tends to infinity, the smaller term goes to infinity, then the larger term has no other option than to also blow up to positive infinity. So we now have shown that in the limit as n goes to infinity, Sn also goes to infinity. But let us write this now without the limit. So if we rewrite Sn in its summation form, being the sum of 1 over n from 1 to uppercase n, well, as n tends to infinity, the upper bound of summation goes to infinity. So we can rewrite this as we would an improper integral, summing from 1 to infinity of 1 over n. And if we write this in expanded form, then we get 1 plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, and so on. And again, because now the upper bound of summation is infinite, the summation never ends. We have an infinite sum of positive terms. And we have just shown by comparing Sn to the area below the curve 1 over x, that this infinite sum is actually equal to infinity. So it is impossible to sum all the reciprocals of the positive integers. As you keep adding more and more of the terms, the sum will keep increasing without bounds, and so in the limit, it blows up to positive infinity. And this infinite sum is usually called the harmonic series. And that's it. Okay, so in this video, we will sketch and graph the following function. So, of course, we will need to find the first and second derivative, so let's do so. And of course, since we're going to look for critical point and inflection points, we need to find where the first and second derivative are equal to 0 and undefined. As both are polynomials, they can never be undefined, so they can only be 0. So that means if you have a polynomial or any type of expression and you want to find its zeros, you're trying, of course, to factor the expression. So we can factor here a multiple of 3. And now we have a quadratic polynomial. We can try and factor with the product sum trick. So two numbers whose product is 3, whose sum is negative 4, those are, of course, negative 1 and negative 3. The second derivative is a lot easier to factor. We can factor as 6. And this completes the factoring. And if we can, when we sketch or graph the function, we try and find the zeros of the function, again, if possible. So we have, again, a polynomial. We try and factor. We have an obvious common factor of x that we can factor out. And we have, again, a quadratic polynomial, so we can try and factor by inspection. If we can, of course, so we would need to find two numbers whose product is positive 9, whose sum is negative 6. This is, of course, negative 3 and negative 3. So we have x minus 3 squared. So now we have the function fully factored, the first derivative fully factored, and the second derivative fully factored, so we're good to go. So first, the zeros of the function. Well, this is now trivial, right, as we factor the function y is equal to 0 if x equals 0 or x equals 3. We usually try to find also the y-intercepts, right? The zeros are the x-intercepts, the values of x where the function crosses the x-axis. So let's find the y-intercept. The point at which the function crosses the y-axis, this is of course trivial. We simply evaluate y at x equals 0. And of course, when x is 0, y is also 0, and we recover the familiar 0 that we have already found. We can now look for the critical points, which I'll label as CP. And again, the first derivative is never undefined, so there are no critical points of the second type, only those of the first type when the derivative is equal to 0. But this is now again trivial as we factor fully the first derivative. This can only be 0 if x is 1 or if x is 3. So we have two critical points, x equals 1 and x equals 3. Let's now find our inflection points, or possible inflection points. Again, the second derivative is always defined, so we have no possible inflection points of type 2, only those of type 1 where the second derivative is equal to 0. And again, as we factor the second derivative, this is trivial. The second derivative is 0 if x equals 2. So we now have the zeros, the y-intercept, the critical points, and the inflection points. What we now have to do is classify those two critical points. So we have to find out what does the graph of the function look like around x equals 1 and x equals 3. And of course, to classify critical points, we will simply use the second derivative to tell us at each point whether the curve is concave up or concave down. Let me put this here. So, x equals 1, x equals 3. So let's put two different x-axes. One for x equals 1, the other for x equals 3. And again, we ask, well, what does the function look like around these 2 points? Well, since those are two critical points where the derivative is 0, at this point the curve is flat, therefore it has a horizontal tangent line in each case. So we know